problem 57 of Neetcode 150, Kate's smallest integer in the BST, the binary search tree. All right, so we are given this problem, and we can see that all here highlighted in blue is basically just a very basic definition of what a binary search tree is. So really, the problem is stated in like these 15 words. So we're given the root of a binary search tree and an integer k, and we have to return the k's smallest value indexed in the three. All right, so let's say that we have this binary search tree. What if we actually just take all the values, we just extract them and sort them in an array? Well, we are gonna have an array of 1, 2, and 3, right? I think you're following me on up to here. And now if we're given the value k1, we're not being told find the index 1, we're being told find the first value, so it's going to have to be 1, all right? Same principle here, okay? So if we take all the values, we just extract them, okay? Like it's going to give us an array of 2, 3, 4, and 5 once sorted, and now they're asking us to find the the fourth one, right? So in our array containing 2, 3, 4, and 5, well, we're just going to take that 5, okay? That's it. So they're telling us that we should aim for a solution as good or better than big O of n time and big O of n space. Okay, so let's see how we can actually solve that. So for big O of n space, what I the best solution here is actually to use depth first search with a stack, because if we don't really have to use breadth first search, because to be honest, we don't really care about the right side until needed. So we don't necessarily have to compute all the values necessary. We have to go to the most left side every single time. This is going to give us the smallest value. Okay, so from here we want to go to the left as far as possible. We have 2, right? So after 2, we have 5, and after 5 we have 16, then we have 17, then we have 35, then we have that value to the left, which is 29. Then it's going to be 38 in the worst case if we have to give the last value. So this is going to give us big O of n, but we might gonna do this more efficiently if the value is like 2, right? So what we're gonna do first is that we are actually gonna go as far as possible to the left until we reach none. Okay, so once we are at 2 and we go again to the left, we are basically gonna get our none, right? Okay, and in the way through this none value, we are gonna add every single value we met to the stack. Okay, so we are gonna create a stack. So we're initially gonna add a 17 followed by a 5. Okay, followed by a 5, and then followed by a 2. And when we once we reach that 2 value, we are simply gonna pop that last value here. So we're gonna take that 2 out just like this, and this value will be our new pillar. So we know that this actually is going to be well, for the first round, it's going to be the smallest value we can think of in our binary search tree. All right, so this is going to be element 1. So if element 1 is going to, if they're asking us to get the first element, we are going to return 2. Okay, but let's say they're asking us for element 3. All right, and this is important, okay, because every time we are doing doing a search and we find a number, right? So now we found the smallest number, then we're going to find the second smallest number, then the third smallest number. We actually have to keep our own count of how many numbers we found so far. So now we have found 2, so we are just going to set our n to 1, and then set they want us to find the fourth element. Okay, so then actually what do we have to do once we are here? Okay, what we're gonna do, we're just gonna pop that value again. Okay, and that value itself, oh, I pop this? No. All right, so let me just erase it then. All right, so we're gonna pop that value 5, and by popping that value 5, we now have a second, we have the second smallest value. So we are going to update our own count of how many values we have, and we are going to ensure that we have this this value 5 here out of this stack. After this, there is a time where we eventually want to go to the right, okay? Um, because right now when we are at 5, we want to go to that 16 value, okay? And it might not be super easy to actually say that go to the right if there is not none, otherwise just go back one. So we are just gonna at the end of our recursive call set the current pointer to the right. So if it is none, well, we are just gonna go well, in our algorithm, at first, when we enter the recursive call, we're going to check if the value is none. So if on the last call, we set that value to be equal to the right side, and it does not exist, well, we are just going to reset our value, our current pointer, to the value that we just popped out of the stack. All right. I think that we should start coding this. So first, what you want to do is to keep track of how many values we popped out of this stack, right? So we're going to initially set that to 0. We are going to create our stack just like this. And we are also going to set our pointer equal to the root. All right. And now we are going to be willing to do a while loop while there is a current and while there is a stack. So you might gonna tell me, yeah, but at some point the pointer is going to be equal to none. Yeah, the pointer will be equal to none many times, but the stack might not be equal to none. So if both are actually equal to none, this is where we know we have to stop. All right, and now this is where we want to create a recursive call where we go, not a recursive call, sorry, but we want to actually go to the left as far as possible until we reach a non-value. So we are going to basically set while there is a pointer. And what do we want to do while there is a pointer? First, we want to add to the stack that 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 node where the pointer is, and then we want to make sure that the pointer goes to the left. So we are going to say this pointer dot left. All right, and once we actually break that loop, well, it must mean that we reach we reach a non-value. So if we reach a non-value, it means that the last value that we added to the stack is actually the smallest value in our binary search tree. So we are just going to set back our pointer to the stack, the top value of the stack, which is retrieved like this, right? And then it also means that we found a value. So we have to increment n by 1. And then we can, once we have our n incremented by 1, we are going to check if n is equal to k. And if it is equal to k, where this is where we actually want to return that value, okay? All right. And now this is the place where we have to check to the right. Okay, so once you actually reach the smallest element, let's see if we are at 2. Okay, we are just gonna blindly say set that new pointer to the right. Okay, whatever that thing is. If it is not a value, if it is none, well, we are just gonna skip that while loop here, and we're gonna go set our pointer back to the top value of the stack. So at this point, the next top value will be the 5. Okay, so we are just gonna set back, or we're gonna set our pointer to the right. So we don't take any risk like this, and we can actually go visit every single node. All right, so that's really it. We don't even need to return anything at the end. Let's just submit this, see if it works. We got an error. Your output was none, but was expecting a type hint. Okay, so let's see what might have gone wrong here. Right, so the error here was actually quite simple. Instead of using it and we have to use it or, because basically after this run, right, when we set a pointer to pointer at right, well, the pointer might actually be none. So if we actually have a pointer with a value and a stack, it means that something's off, right? Because we're giving you a pointer that is none, and we know there is a stack, so we want the algorithm to be smart enough to know that even though it is none, there might be something in the stack, and if there is something in the stack, then pop that value and take that value. Okay, so we have to use that or statement. All right, and there you go. All right, so I hope you learned from this video, and I hope to see you in the next one.